All right, so welcome to the last day of statistics. Yay! Or, oh, it's the last day. No, it's yay, it's the last day. So today is our last day, and we're going to spend today kind of reviewing for the final exam, getting ourselves ready, um, reminding ourselves what we've talked about because it's been a long quarter. We have talked about an awful lot of stuff, and so it will be useful for us to have that kind of up front in the top of our head. And I think probably one thing that's going to happen as we're going along is we'll probably talk about the exam. Just so you guys know, I did grade exam 2. Those scores are in. Hopefully you saw my comments. But we'll talk a little bit about that in the context of reviewing for the final as well. All right. So, but other than that, I kind of want to turn it over to you guys. But let me start as we always do, which is, do you have any questions on the homeworks? Anything you'd like to talk about from regression? Because I think that's pretty much the only thing that's still outstanding, right? How's regression going? Is it making sense? Are you seeing how it works? All right, I'm getting a couple of thumbs up. Got Ashton and Carolina Alley. All right, good. So, oh man, thumbs up everywhere. Whew, calm down. Well, good, because regression, I mean, if you're comfortable with the idea of just linear graphs, like what it means to have a line, regression's not that weird or crazy. And it really is just, we're trying to build a model that's the best predictor of what we've got, right? And I will tell you, I think I hinted at it, that there are all kinds of other regressions. I come from a science/math background, and regression is huge in the sciences because when you're, if you're out there and you're studying, the population of fish in, the Chesapeake Bay, you're going to have data points and you're going to plot all these data points and you're going to try to make sense of it. And the way we do that is with regression. So it is kind of a big deal. But good. It sounds like we don't really have many issues there. So I think what I'm going to do is maybe just start us off, kind of get this ball rolling by talking about or reminding you all of the things that we talked about over this quarter. It's a long list, right? I mean, it's only been 3 months. It probably feels like more than 3 months, and there's been an awful lot of stuff. But since the final exam is cumulative, since it does cover everything, it's probably a good idea if we sort of just refresh our memory because I don't know about you, but January was a long, long time ago. All right, so basically what I'm going to do is just sort of go through the book. I mean, I'm not like going to read you the book, but I'm going to kind of go down the list of what the topics were and what we ran into along the way. So chapter 1 was all just setting the table. It was getting us, familiar with the terms of statistics, the goal of statistics. So there we really talked about things, like data, sampling, how we do sampling, the actual statistics that we use, the numbers that we use, things like mean, median, mode. We had frequency tables, right? And so that's really what the beginning of this class was. So some things that you should definitely be able to do. All right. And we could even probably build a little bit of a sample exam as we go here. But really from the first chapter, it's know the terminology, right? That's where we learned the things like the different types of sampling. You may remember words like stratified, cluster, convenience, random, right? So definitely know the different kinds of sampling and be able to recognize them. A good tool for that, go back to, I think it was quiz 1, and I know for sure it was on exam 1, where I gave you, just saying where it was like, okay, this is how we sampled, match it to the type, right? So those would be good things to go back and look at, just to kind of refresh your memory, to remind yourself, oh yeah, convenience sampling is exactly what it sounds like. I'm just, grabbing people because they're all coming out of the grocery store, or I'm asking the people in my class because I can access my classmates, right? That's convenience as opposed to systematic. All right, every third person that walks through the door, I am going to measure their height, right? So that's very systematic and things like that. So know your terminology. That's really what comes from chapter 1. Chapter 2 was where we actually started calculating things and doing things, right? And so stuff in there, again, were the, be able to calculate means, medians, modes, quartiles, maxes and mins, percentiles, and things like that. All right, so chapter 2 is what we call descriptive statistics. And that's exactly what it sounds like. Those were the numbers that we used to describe sets of data. So things that you should definitely be able to do there, calculate those things. I think by now you're probably good with, I hope you're probably good with using the calculator to get values, to put in data and have it spit, do the one variable statistics and all that to get means and standard deviations and whatnot. But just remember what mean is. At this point, you guys know, right? Mean is the average. Median, do you guys remember what that was? Can anybody remind us what the median of a set of data was? All right, so Ali just said the middle. Good. Yeah, think median. Think middle. And it is literally the middle value. If you were to list all the data from smallest to biggest, the median was smack dab in the middle. If there wasn't a number that was smack dab in the middle, you find the mean of the ones on either side of where the middle would be. So that happens when you have an even number of data points. Okay, good. Good job, Ali. So then what about mode? Because that was the other one we used. What's the mode of a set of data? All right, good, Willie. Most common. It's the one that shows up most frequently. That's our mode. So for some of you, you might be sitting here going, oh my God, I don't remember those things. Well, that's why we're doing this, is to kind of bring that back into the forefront of your mind. All right. And this can also point out things that you should work on when you study, right? As I'm talking through this list, and if I say something and you're like, whoa, what is that? Two things. One, ask me, say, hey, you just said this word. I don't remember what that is. Because then I can fill you in. But then also that really targets what you need to study. Because what I've found in my forever teaching is that people, not just, not you guys, this is a general people, we all think we kind of know more than we actually do. Right? Where we're like, oh yeah, no, like I'll say, oh, you just got to find the quartiles. And you're like, oh yeah, I know quartiles. But then I give you a problem that says, find the quartiles. And you go, wait, what? So sometimes we tend to overestimate what we know, right? This can help you there. If I say something, you might go, oh yeah, I definitely need to go back and study that. Anyway. So mean, median, and mode, know how to calculate those things. How about quartiles? What were the quartiles? Because there was a first and a third. We call them Q1 and Q3, but what were they? All right, so Bruno just put 0.25 and 0.75, which Willie then followed with 25th and 75th percentiles. Okay, good. So think about what a percentile is. If we talk about a 25th percentile, that means that 25% of the data is less than or equal to that data point. So again, if we make the list from biggest to smallest, the first quartile is where if we go on that spot, 1/4 of the numbers, 1/4 of the data is below that. So I like to think of them as the medians of the top half and bottom half, because I already know how to find a median. That's easy. If I want to find the quartiles, I just do the same process, just looking at, all right, after I find that median, split it in half. Let's look at that top half. Find its middle spot. That's the third quartile. Go to the bottom half. Its median. That's the first quartile. Right? So we have quartiles, and then percentiles are just in general, same idea, but we're not specifying 25 or 75, right? You can have the 90th percentile, the 27th percentile, it doesn't really matter. Okay, so for sure, be able to get those numbers, whether you do them yourself or you use technology to help you. Both are going to be fine. When it comes to the final exam, I full on expect you're going to use technology to do these things. I'm not really looking to see, can you do calculations by hand? Because that's not the point. Like really in statistics, if you haven't figured that out, in stats, we're not all about using the formulas, plug in numbers, and do everything by hand, right? We do whatever calculations we need to at the start so that then we can ship it off to technology and say, here you go, computer, do your business, spit back the answer to me, right? But we got to make sure we're telling it the right thing, because technology is awesome. I mean, your calculator, your computer, great things to have. But the problem is they're really dumb. They're really dumb. They don't know how to think. Side note, that's probably good, because when they start thinking, that's when like Skynet happens and Terminator and, you know. But computers are dumb. But they're really good at following instructions. All right. So they're going to be as good as you are telling them what to do. So as long as you know what to input, please feel free to use the technology. The one thing I am going to say, though, is when you do this on the exam, make sure you tell me what you do, because otherwise I can't really give you partial credit. And you may have noticed that on the exams, I always say, you know, if you use technology, be sure you tell me what steps you're doing. I just want to reinforce that, because if I'm grading something and I say, let's say I ask for a box and whisker plot, which means you got to find the quartiles. And so you draw it, and then your first quartile is like way off. And if all you've done is draw that plot and not explain to where that came from, how do I even give you any credit? It's wrong. I can't even see your thought process. I can't even see, oh yeah, no, you were doing the right thing. You just, you know, typed in a number wrong or something like that. So just make sure you explain yourself, communicate with me. It makes it just so that I know what you're doing. And that way I can assess your knowledge a little bit better. Anyway, so from chapter 2, for sure, know how to find median, mode, quartiles, means, all that. Be able to draw the box plots, right? Be able to do the box and whisker plots while we're here, because I don't know if all the plots were in chapter 2, but know how to do all the various kinds of graphs that we've seen, right? Know how to do box plots, know how to do stem and leaf plots, know how to do frequency charts, frequency graphs. Those were like histograms, remember, where you make the bars that are as tall as how often those things show up. Know how to do scatter plots. I mean, we just did that when we were talking about linear regression, because graphs are really important in statistics. So I'm just curious, that this is not, there are no points on this or anything, but give me a thumbs up if you've ever actually looked at an academic paper, right? So from a magazine or something, an academic paper that used statistics. Give me a thumbs up if you've done that. Okay, so just about everybody has done that. Okay, now if you go back and you actually look at that, so even something as simple as go look at a like science journal. Science is one that's not really technical. It's sort of the Reader's Digest of science journals. It just sort of gives you the highlights. I mean, it's great if you want just a little taste of everything. But if you go and you look at that, they will show statistics, but they will always have graphs. Always. Because so many people are visual learners. I know I am. You show me something, I'll remember it forever. You just describe it, maybe not. And so in statistics, we do that. You'll always see graphs accompanying your data. Anyway, so know how to do the different kinds of graphs, because I could potentially ask you to do that. I'm going to ask you to do that. All right. So that's what number 2 was just all about describing our data sets. I think I should probably mention standard deviation, because that's also a descriptor, right? Median, mean, median, those tend to tell us our middle spots, and then standard deviation was the spread. Please do not try to set that formula for standard deviation in your brain. Don't try to calculate it. Use your technology to find it, because that sucker is gnarly. Okay, so that was, I mean, we're talking January, right? Early January. That's what we were talking about, just setting the table with here's how we describe statistics. All right, and then at that point, we sort of changed our, well, we definitely changed what we were looking at. We started looking at probabilities. I'm going to guess that this is probably the topic that you least remember, the topic that is probably going to be the most challenging right now before actually going back and studying it, because we haven't done much with it in terms of calculating probabilities. We talk about probabilities all the time. Think about every time that we do some sort of a hypothesis test, and we get that P. I mean, you've even heard me say, oh, well, this would mean that it's a 5%, chance that this would happen randomly, blah, 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 right? I'm talking probabilities, but we haven't actually gone and calculated them since late January, early February. So I definitely recommend you go back and look at this, because it's probably one of the things that's least fresh. But really think about what probability is. Probability is a measure of how likely something is to occur. Probabilities are always between 0 and 1. 0 means it can't happen. It'll never happen. Right? Probability of 1 means it's gonna happen. Right? Like the probability that I will someday die. 1. I'm gonna die someday. Right? The probability that I will give birth to another human, 0. Right? I can't do that biologically. All right. So there are things that have 0 probability. There are others that have 1 probability. And then of course there's anything in between, right? What's the probability that I trip and fall down my stairs the next time I'm going down them? Well, it's not 0. There's the possibility I'm going to trip and fall. It's not 1, because it's not assured that I'm going to trip and fall, right? But it's somewhere in between those, hopefully closer to 0. All right, so know how to calculate probabilities. And to do this, it sort of depends how we're given our information, but it's always the same. It's always, if we want to think about number of outcomes, it's always the number of ways that our specific event can occur, that goes on top, divided by the total number of possible outcomes. right? So like when we were talking about rolling dice, what's the probability of rolling a pair of dice and getting a 6? So you would count a total of 6. So you'd count up all the different ways that can happen. 1 and 5, 2 and 4, 3 and 3, 4 and 2, 5 and 1. Right? So there's 5 ways of doing that. And then you divide that by the total number of possible results when you roll 2 dice, which was 36. So the probability of rolling a total of 6 on one throw of the dice is 5 out of 36. It's even easier if we've got a contingency table. Those are, you should be pretty good with contingency tables because we keep seeing them off and on, right? But again, you just look for the number that you're interested in divided by the total. So that's the basics of probability, but there were all kinds of different types of things that you should know. So be able to do regular old probabilities, but also be able to do probabilities and probabilities or probabilities. Know how to do probabilities when you already know something has happened, right? Those are the good old probability of A given B. So we call those conditional probabilities. So I would definitely go back and look at those and practice probabilities, because I am going to ask you on the final, I can guarantee you there's going to be a problem or maybe two that are, here are some events, calculate the probabilities, some combination. So a good place to review that, for sure, again, exam 1. And I'm going to guess probably quiz 3, maybe. I don't remember exactly what's on each quiz. But the good thing about the fact that we've had regular quizzes is that you can go back to those and see the kinds of problems that we did back in the day. All right, now I would consider that probability chapter as, again, just setting the table, because we needed to know probability before we moved on. So once we had sort of the definitions of stats, we knew what all those things were: mean, median, mode, standard deviation, and we talked about our probabilities. That let us get to the key of statistics, which like the core, which are the probability density functions. So those were the PDFs, and probability density functions are exactly what they sound like. They're the functions that tell you the probabilities that certain things are going to happen. So we talked about a whole bunch of them. We broke them into 2 pairs. There were discrete probability density functions and continuous probability density functions. So the discrete were the ones that are countable. Anytime you see the word discrete, think it's got to be something that's countable. So that would be like the outcomes of rolling a pair of dice. That's countable. I know exactly what the different results are, and I can count them each, right? As opposed to heights of people. Heights of people is not countable. There's, a wide variety, and you can get all kinds of decimals and fractions and all that. So there's a difference between discrete and continuous. But in terms of the discrete, the big ones that we talked about in terms of the probability density functions were the binomial. That was by far the biggest one. Binomial, that was the one where there are only 2 options, right? We ask the question and it's yes or no, right? Are you married? Yes or no. Do you own a dog? Yes or no. Are you taking an English class? Yes or no, right? So anything that just has 2 options, so you can think of yes or no, that's what we call a binomial distribution. And so that had its own way of, it had its, each distribution has its unique way of getting probabilities, and binomial definitely had one. And for binomial, what was really important was knowing the probability of success, right? Like, what's the probability that if I ask somebody if they own a dog, what's the percent likelihood that occurs, right? We need to know that. And then we need to know how many people we're asking. And once we determine that, everything is set, and we can now calculate probabilities. So that was the big one. We also talked about geometric and Poisson. I'm just going to tell you right now, the only discrete probability density function that I want you to know about is binomial. Okay. I will ask you a binomial distribution question. I will not ask you geometric. I will not ask you Poisson. All right. So again, the only discrete one that I care that you know is binomial. So go back and review it. Make sure you understand the commands for your calculator. Those are the ones, remember, the PDF and the CDF. Make sure you know how to do that to get your various probabilities depending upon what you're trying to do. But that was the big discrete one. When it came to continuous, there were a couple that were kind of important. So again, remember, continuous is, they're not just like countable, it's any possible thing. There really were two big continuous probability density functions. And again, these are the two that you need to know. The first is uniform. All right, so hopefully you remember uniform. That's the everything is just as likely. And so those graphs, the graphs of those were nice horizontal lines. So you know the uniform distribution, and then know the normal distribution. Now, when I say know them, I don't necessarily mean know all the formulas to calculate everything. Because again, like normal distribution, I don't care that you know how to calculate standard deviation, but I expect that you know how to get it, right? Which that's going to be a technology thing. For like the uniform, it's probably easier just to use the formulas, because like calculating the mean of a uniform distribution is easy. I don't know if you remember how to do that, but basically, like for a uniform, if you got your two endpoints, you're going from A to B, the mean is A plus B over 2. That's just the average of the small and the large. So like that's easy. The standard deviation is not as easy, but it's a pretty quick formula. Anyway, so when it comes to continuous, I only expect that you know uniform and normal. But for the continuous, finding probabilities is a little bit different. Now we're looking at areas under the curves, which in general, we need more math than you guys have to do that. You need calculus. But even there, sometimes the calculus is a little bit rough on these. But at least just know the idea that the probability is the area under the curve between the values. But just be able to deal with them, be able to use them, do your calculations with them, know how to access the stuff in the calculator or computer to do them. All right, so that was just about the halfway point of the class, believe it or not. It already feels like a lot of information, and it was. But that was about the halfway point. Okay, so then we really turned our attention to something different, and that was using these probability density functions. But for the most part, we did the same thing always. For the most part, what we were doing is we were testing hypotheses, right? So there were a couple more chapters to sort of set up hypothesis testing. The first one was the central limit theorem. And that one basically just says that if you sample and you do lots of samples, the values that you get from the samples, like the means that you get from the samples or the proportions that you get from the samples, they start following the normal distribution. So then we can go back and use normal distribution to do stuff. Right. So that was the idea behind the central limit theorem. But do you realize that there were a couple of variations? There was the central limit theorem for the sample means, but there was also the central limit theorem for the sample sums. They both led to normal distributions, but they had different standard deviations and different means. All right, so definitely go back and review those, because that was definitely an issue that happened on this most recent exam. You may remember there was the question about the bears. We were sampling bears and looking for, I think it was the probability that the total weight of the bears was between whatever numbers. You got to be really careful when you do those problems. You got to read them really carefully, because if it says, say, total weight, that means you have to do the one with the sums, so that your mean is going to be your n times the mean of the population, and your standard deviation is going to be the square root of n times the standard deviation of the population, right? As opposed to the average weight of the sample. That would be then central limit theorem for sample means. So much of it is just watching the wording, right? But we talked about the central limit theorem, and then we talked about confidence intervals. And confidence intervals, just know how to find them, use the formulas. For the most part, I think that problem on the quiz or exam, everybody did fine on. Very few issues with the confidence interval. Okay, so with that, we then started doing hypothesis testing. And that's what the next like 3 or 4 chapters were about. And so I kind of want to talk about them all at once, because hypothesis testing, it's all the same. It's all the same. You create your null hypothesis. All right, how that's created might be a little bit different depending on what we're doing. But you create your null hypothesis and you create the alternative hypothesis. The null hypothesis is always equals, right? It's always in equals. The alternative hypothesis is not equal, but it can be not equal, it can be greater than, or it can be less than. Which one you pick needs to match what you're testing. And this was an issue that happened on the exam. For example, you may remember the one about finding the amount of financial aid that Lake Tahoe Community College students get. And what we were curious about was that greater than, I think we said California, right? So do Tahoe students get more financial aid than the rest of California? So because we're looking for, do they get more than, you want to have an alternative hypothesis that's the mean is greater than whatever the number is we're looking for. So always match that up with what you're testing, right? If the thing says, we want to know if it's different for this group. Okay, so different, not equal. That's what our alternative hypothesis is going to be. And it's super important that you have that correct, because when you punch that into your black box, right, when you go to your technology to do the hypothesis test, that's one of the things it asks you. And you get very different results depending upon which you do. Usually, the not equal leads to two-tail test, and the two-tail test cuts your p-value in half, as opposed to a one-tailed test, which would be greater than or less than. And so just think about that. Like, let's say your p-value is 0.06. Well, that if our alpha, say, was 0.05, that p-value is greater than 0.05. If we cut it in half, 0.03 is now less than 0.05, and we have completely different conclusions. So super, 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 super important that you set that alternative hypothesis so that it matches what you're trying to test. Okay. Anyway, so we create our hypotheses, then we put our stuff into the calculator and we tell it, do the test. Now, that step, there's a little bit of a challenge there because there are so many different tests. So let me just kind of remind you about them. So if you just have one sample, then you're going to do either a z-test or a t-test. You do the z-test when you know the population standard deviation, and you do the t-test if you don't. All right. But again, that's only if we have one sample. That was another issue that happened on this exam. Take, for example, that one of LTCC students getting financial aid compared to California. A lot of you tried to do a two-sample thing because you're saying, oh, we're comparing the Tahoe students to California students. But the California students, you didn't have a sample. You were told about them. You were told what their mean was. You were told, I think you were told their standard deviation. If you weren't, then that just changes the T or to a t-test. But you weren't given a sample. So when you choose your test, look at what kind of sample do I have? Not what am I comparing it against? What kind of sample do I have? Okay, so one sample, you're either going to do a z-test or a t-test if you're doing means. If you're looking for proportions, what percent of people are vegetarians or whatever, then you're going to use the prop test. So you're going to use one prop z, the one because you got one sample, right? So one prop z. If you're comparing two samples, so now I've got a sample from LTCC and I've got a sample from Modesto Junior College. And I'm going to compare these two. Now we're going to use a two-sample test. And you've got the two-sample z-test and the two-sample t-test. And again, you decide the same way. Use the z-test if you know both of their standard deviations, the population standard deviations. If you don't, use the two-sample t-test. And then if you're going to check proportions, it's the two prop z instead of the one prop z. So you got those, but then we also have the chi-square, the one that we most recently saw. But remember, we do that just for some specific types of things. One is goodness of fit. How well does this data actually fit our guess at its distribution? So you use the chi-square there. You can also use it as a test of independence, or test of dependence, I should say, to see if two quantities are dependent, the way that probability suggests. And you can also use it as a test of variance, right? Test of homogeneity to see if proportions are actually the same over a whole bunch of different choices. So really, when it comes to hypothesis testing, you have to get the right test. Even with regression, right? We just did regression and we saw that there was a regression hypothesis test, but it was used in a very specific situation as well when we're trying to find a line that fits our data best. So my recommendation with those, practice them. Go to the book and randomly pick some. The end of the chapters have some like practice problems and all that. And so maybe you can even get some where you don't know what section they came from. Because if you know what section they come from, then you might have a little bit of a, oh yeah, this one's supposed to be a, a t-test or whatever. But if it's just random, what is this one? What is it telling us to do? That's some good practice there. All right, so hypothesis testing. So we put it into our box and we say, do your thing. We just got to make sure we're telling it to do the right thing. But then what pops out is a p-value. And regardless of what test we're doing, we do the same thing. If that p-value is bigger than alpha, we fail to reject the null hypothesis. We just say, hey, we don't have enough information. We can't say that the null hypothesis is wrong. Or if the p is less than alpha, then we do reject the null hypothesis. And there we say, you know what? We've got enough information. It's statistically significant information that the null hypothesis isn't true. Boom. And it's gone. But again, it doesn't matter what test you do at all. All right. I actually love hypothesis testing because there's not a lot of work to do. You guys might disagree, but really what it comes down to is, all right, let's read it. Let's recognize what test to do. And once I figured out that test, all right, I'm going to do a 2 prop Z test on this data. Go. Oh, hey, P equals. And I just like a key in on the P. I look at that P value. I compare it against alpha. And I'm done. Is it bigger than or is it less than? Well, then I know either I reject the null hypothesis or I fail to reject it, and I'm done. So, excuse me. It's kind of nice that once you figure out which test to do, you don't have to think anymore. Okay, but you got to get the right test. Super important. All right, so, and that was basically the last few chapters were all about hypothesis testing and recognize which one. And then obviously this very last chapter on regression, be able to find regression lines, be able to, do the hypothesis test and all that. So some other things that are going to be on the exam, I promise you. I'm going to give you data and I'm going to say, find the best fit line to this. Right? Do the linear regression. I am going to give you a few, probably like 4 or so, 4 or 5 hypothesis testing questions where you're going to have to, figure out the validity of whatever the statement is. When you do hypothesis testing, and I'm going to tell you to do this with each one of them. Make sure that you tell me what test you do, right? Tell me what test you do. Tell me your p-value. Tell me then what that means with the null hypothesis, either reject or fail to reject. But then most importantly, in words, tell me what does that mean for this problem? What does that mean for this situation? So if you look at my comments, you'll see where I'll write something like, what's your conclusion in the context of this problem or whatever. And what I mean by that is, if your null hypothesis was that LTCC students get the same amount of financial aid as other California students, you reject that null hypothesis, what you're going to want to say is something like, there is statistical significant evidence that Lake Tahoe Community College students, get more financial aid than California students, right? That's what it means to reject the null hypothesis in that problem. And the reason that that's important is someone who's looking at, like, pretend that you're making this report for your boss or something. They don't necessarily know what the null hypothesis is. So if you just say, oh, hey, boss, we got to fail to reject the null hypothesis, they're going to look at you and be like, what the hell does that mean? Tell me what I need to know. Oh, okay. What that means is we don't know that blah, 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 right? So you need to make that extra step. Just write it down in words. It's like one sentence to make it clear what's going on in the context of that problem. Okay, so let's see if we kind of have an idea of what this exam is going to look like now. So there's going to be a linear regression problem. 4 or 5 hypothesis testing problem. There's going to be something about confidence intervals. Either find me a confidence interval, figure out how many people you got to get for a certain confidence interval, something like that. There's going to be a central limit theorem question. There will be a question about just general, like the uniform distribution, some sort of probability, something with uniform distribution. There will definitely be a binomial distribution problem. There will be a calculate probabilities kind of problem, most likely with a contingency table. I like contingency tables. They're really visual. There's going to be, here's a data set. Tell me things: mean, median, mode, standard deviation, quartiles, percentiles, right? So there'll be something like that with a data set. It could be just a plain old data set, or it could be a data set with frequencies if I give you a frequency table. But either way, so definitely know how to do that. There will be a question or two on terminology, right? Know your various terms, like on different kinds of sampling or things like that. Well, there you go. That's what the final exam is going to look like. I mean, it's not like I'm going to pull something out that you've never seen before. You've seen examples on exams, on quizzes. You've done a bunch of homeworks on them. So you kind of know what to expect, right? Exactly what they're going to be, I don't know, right? I don't know. Am I going to ask you to do, have something that makes you do a t-test versus a z-test? Well, I'll figure that out once I write it. Are you going to be doing some two-sample thing with proportions? Maybe not. Maybe it's going to be a two-sample thing with means, or I don't know. But that doesn't actually really matter, right? You just have to be able to recognize it so that you can put it into your calculator and let it do its thing. Anyway, so there's a lot of stuff we've talked about this quarter. There's an absolute ton. But let me just give you a little bit more advice in terms of the exam and everything. So it is take home, right? I mean, you're doing it at home. It is timed, but you're doing it at home or wherever you happen to be. So make use of your notes. It's totally fine to have your notes. So one thing I would recommend is maybe condensing your notes, like going through your notes and finding the key important things and kind of sifting that out. Like maybe have a sheet where you've got hypothesis testing. And then below hypothesis testing, you have here are the general steps, right? Or maybe even a little flow chart. Do I have one sample or do I have two samples? Okay, so one sample. Do I know the standard deviation of the population? Yes, no. Okay, yes. Ooh, z-test. No, t-test. Right? Am I finding a proportion or a mean? Right, so just get it organized so you've got something pretty quick and easy to look stuff up. Because if this is your notes for the entire class, you don't want to be going like this, trying to find the one piece of information you need. You want to do that, well, you don't want to do that during the exam. You want to do that ahead of time so that this is your notes. And you just go, oh yeah, okay, this is what I need to do. So that's another big recommendation I have, since this is a take-home kind of thing where you can set up and be good to go. Anyway. Okay, so with that, I mean, there's your general outline, and we still have some time. So is there anything in particular you guys would like to talk about? Any examples you'd like to see? I'm totally cool with whatever. If what you want to do is just be like, let's be out of here, that can happen too. All right, so because this is your time, you guys know what you need. So just let me know. Shout it out, put it in the chat box. If you just want to bounce, go for it. If I start losing a lot of people, I'll just call it.
Can we go over confidence intervals?
Totally.
Because I'm not very good at confidence intervals, and I'd like to be a little more like prepared for it for the exam.
Okay, we can definitely do that, Ashton. Thank you.
Okay.
Do you want to do like we try to calculate a confidence interval, or find a sample size we need for a specific kind of?
I like. Can we go over sample sizes? Because I wasn't really good on that in the last exam, and
Sure.
you know it's the final, so I'd like to be better at it.
Yeah, no worries. Okay, I think that totally works. We can do that. I'm going to go ahead and start getting one of those open here. While I'm doing that, anyone else have something they want to see, talk about? All right. Doesn't sound like it. Okay, so let me go ahead then and. All right. Yeah, you're welcome, Carolina. See you later. And I think I missed saying goodbye to Bruno, but yeah, good luck on your finals. And I will be around, obviously. You can send me messages and stuff. All right. So let me pull up my open math here. And let's see if we can find one where we have to actually calculate a sample size. Of course, I picked one that doesn't have sample size. Let me stop share on this again. Go find one that does.
That's valid.
You guys know how it is. Let's see. Oh, there we go. This will do it. All right, and actually, Ashton, you know what? I'm going to pull up your homework set.
Oh no! Okay.
No. Don't worry. No one will see what your score is.
No, it's okay. I just know
But,
I didn't do very hot on the sample size one.
But we'll, this way, Well, it's probably going to give you horrible flashbacks, and I apologize for that. That's not
No,
what
it's
I'm
okay.
thinking
It's
here.
okay.
All of a sudden, Ash is like, "Oh my god!"
It's just a lot of work, and my brain doesn't really know how to comprehend like how to do all those steps in one. Because I do really love the hypothesis testing because it's mainly on my calculator, and I know how
Mhm.
to like set it up and then like figure it out and do it on my calculator. I don't know how to
Right.
do simplifies.
Yeah, it's kind of like what I was getting at, right? Where if you know what to
Yeah,
tell your calculator to do, yeah, it's easy. You just let it go.
yeah.
Okay, so let's look at this one, number 2. So it says you want to obtain a sample to estimate a population proportion. So first of all, look at the wording, and this is kind of telling you what you're trying to do, right?
Mm-hmm.
Like it says we're obtaining a sample, and it's a population proportion. So the proportion matters. That's kind of a key term there too, because there's a difference between what we do when we've got means versus proportions. We use a different formula. Okay,
Okay.
so some keywords again. Let me just sort of highlight it here, right? So we're obtaining a sample, but we're going to estimate a population proportion. So you see the word proportion, and immediately your brain should go, "Oh, okay. I'm going to use the proportion formula."
Okay.
The proportion formula, that was the one that had the p hat and the q hat,
Yeah, no,
right?
that really messed me up, you know.
Okay. So, well, so we've got the 2, so we need to make sure that we go to the right one, right?
Okay.
So that phrase right there tells me I'm going to use the proportion. So then we should start breaking it down. What information do we have, right? So this says, at this point in time, you have no reasonable preliminary estimation of the population proportion. So we don't know anything, right? We don't know anything right now.
Mm-hmm.
But we want to be 80% confident that our estimate is within 3.5% of the true population proportion. Now, we just got 2 numbers. We got 2 percentage numbers, but those 2 play very different roles in the formula. All right, so first of all, this one, the 80%. Notice that what it says is we want to be 80% confident. So that 80% is our confidence level.
Okay.
So can you kind of see how you're going to
Yeah,
recognize
yeah,
this confidence level?
the confident part, yeah, I understand that. Now,
Okay.
it's mainly just the setting it up. Like, that's
Yep.
my issue. And I try to watch the video, and the video is just, like, the video, it helped me. But when I went to do it into, like, Canvas, it just wasn't right. And it really
Okay.
confused me because I did all the steps in the video correct. But apparently it's incorrect. And it
Something went
really,
wrong. Okay.
yeah, no, every time something went wrong, and it was so
Okay.
iffy. I hated it.
Okay. So there's our confidence level, and then the 3.5%. That's our error, right? We want to be within 3.5% of the true proportion. Okay, so that's going to be our error bound. And when we did that for proportions in our book, it's called the EBP,
The
error
error
bound for
bound
the proportion.
proportion. Yeah.
Yep. Okay, so now let's turn our attention to the formula. So what I'm going to do, I'm actually going to switch tabs here. Let me go to confidence intervals. We'll go to the very end. This is the other nice thing about this book is at the very end, it's got like all the formulas and everything.
Yeah.
Every chapter, right? So formula review. So we're going to use the one for population proportions, which is this guy. But if we go a little bit further, here's the one that tells us what we need for our n. All right. So that guy right there.
Mm-hmm.
So let's look at what we're going to be putting into the various places. So the error bound, that one we know, that was given to us as 3.5%. So that's going to go in there for error bound. The P prime and Q prime, those would be the proportions that we expect. P would be the proportion that we're expecting. But in this case, we're not told anything, right?
Yeah.
We're told we know nothing about it. So when you know nothing, you put 1/2 in for that.
Okay.
50%.
Okay.
All right. So if they give you a P, you put that number in. Otherwise, you put in 1/2.
Okay.
Okay. And then the Q, that's the probability that it doesn't happen. So it's going to be 1 minus whatever that one is. So with the unknown, they're both going to be 1/2.
Okay, that works.
Okay.
Because I like would if I wouldn't understand how to do it and like the videos weren't like obviously like getting me the right answer, I'd go and search for it on the web
Mm-hmm.
as one does, and it would give me all these like wild steps that I would do. Like I do all of them, you know how insane that is. I do all those steps, and then it would just end out wrong still. So it was like my work was useless.
Yeah. All right. Well, let's see if we can tackle this guy. So I'm going to rewrite that
Okay.
formula right here. So it was n equals z of alpha over 2 squared times p prime times q prime over EBP squared. All right. So let's start putting things in for our specific problem. I'm going to leave the z for a second. Okay, there's going to be a number there, but we'll leave it for right now. But the p prime, we're going to let that be 0.5. And the q prime is also going to be 0.5. Again, because we know nothing about this sample.
So they're just going to be half, yeah.
They're just going to be half. Okay, so then for the error bound for this guy, we're going to put 0.035. And I don't know what happened with you specifically, Asha, when you did these, but one thing that does happen with students a lot is they forget to change that percent to a decimal.
Mm-hmm.
Right? We were told to be 3.5%. And if you just put 3.5 there, you're going to be off by a lot. So you need to make sure you convert it to decimal. So I don't know if that's what happened to you, but I'm just going to throw that out there, especially since some people might be watching this video. I guarantee you that applies to some folks out there. Okay, so far so good. Mm-hmm. How you feeling? All right.
I'm good. Yeah.
Okay, I'll take it. So now let's worry about this z of alpha over 2. Okay, well, we were told alpha was our confidence level. And for this one, it was 80%. Right? And so alpha over 2 is going to be 40%. So when we talk about the z alpha over 2, we need to know what z-score gives us 40%.
Okay.
So what's the z-score of 40%? So this is where we're going to have to do the inverse norm business. So we're going to go to our calculator and we're going to do inverse norm because it's a normal distribution because we're getting a z-score. For the mean, we want the mean to be 0 and the standard deviation to be 1. The reason I'm writing the little symbols there is because your depending what calculator you use, you might put it in a different way, different order.
What did you say the standard deviation was? Sorry, I'm writing this down right now as we
That's
go.
fine. No problem. Standard deviation is 1.
Okay.
The mean is 0. The standard deviation is 1.
Okay.
And then we're going to put in 0.4 or 40%, depending upon what your specific calculator does. So I'm just curious, when you do, what kind of calculator do you use, Ashton?
I have a TI 84 plus.
Okay. So it looks like what I do when I pull up my thing on the computer.
Yeah.
Okay. So I'm going to go ahead and do that. Let me go ahead and pull that up and we'll walk through the steps on my emulator. So let me switch the screen here real quick. All right. So do you remember where to get your inverse norm?
Yeah, it's that right. And then you move over to the test.
I think it's actually under distribution.
Oh, yeah. You,
And so, yep, there it is. So we got inverse norm. Okay, so the area we want is 0.4 because that's half of our 80%. All right, and then the mean and standard deviation are actually already set the way that I want them. I want a mean of 0, standard deviation of 1. All right, so we'll just do enter. Oh, are you kidding me? My calculator just froze up on me.
oh, no.
All right. Well, here's what we'll do. Let me stop sharing for a second. All right. Well, anyway, so you're going to get that number.
Mm-hmm.
And then that number is what's going to go into that spot. Okay. Oh, cool.
Yeah,
Willie.
I did too. It's okay.
Okay. So 0.2533.
Yeah.
That's what you got too, Ashton? Awesome.
Yeah.
Thanks for playing along, guys. I appreciate it. So let's go back to the whiteboard then. So, all right. So you got that it was a negative 0.253. Was that right?
Mm-hmm.
Okay.
Well, 533, but.
Okay. Okay. So 2533.
Mm-hmm.
All right. Now, the fact that it's negative, positive doesn't really matter. You can put the minus in here or the plus in here. It's going to turn positive because when you square it, it's just positive. So I just put the value. I just go, okay, it's going to be 0.2533. So there's our z-score that corresponds to alpha over 2. So you can see how if you change your confidence level, that number is going to change. If you want to be more confident, oh, you know what? That's not the right number. Hold on a second. I just realized the alpha isn't 80. The alpha is 20. It crosses off. And I apologize. This really sucks that I just did this. Okay, the alpha is 20 because this is the chance of us being wrong. If we're 80% correct, we want 20% wrong.
Okay.
So alpha over 2 is going to be just 10%.
Okay.
So let's go back and change that real fast. So this will be the race. Who can get me the z-score for 10% the fastest?
Well, it's just 0.1, right? Like.
Yeah, so instead of 0.4, you're going to put
It's just 0.1.
All right, so Willie got us 1.282. It would be awesome if you could confirm that, Ashton, but
yeah, it is.
Okay. All right, so that's the number we're going to go with. 1.282. All right. Anyway, so what I was saying as I got there, because I realized I was like, that number is way off. If you change your confidence level, this z-score is going to change. Right? If you want to be more confident, that z-score has to get bigger. So you're catching more. Right? But now we're ready just to do this with our calculator. So let's see what we get. So we got 1.282 squared times 0.5 times 0.5 divided by 0.035 squared. And my magical black box told me 335.413, blah, 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 blah. All right, so you're going to get what you get from this calculation. But if we go and we try to put this into the homework and get our answer, it's going to tell us we're wrong. Why can't we put that in as an answer?
Oh, because I don't know. I don't know.
Okay.
I just got to admit, I don't know.
And that's cool. I appreciate that because it's good to know what you don't know. But I don't know if you saw in the chat box, Willie just put, it needs to be a whole number.
Yeah.
Right? So we actually need a whole number. So instead of 335.4, we're going to put 336.
Okay.
Because you're always going to round up. Yeah, exactly. Well, just put that with an exclamation. Round up. Always round up. Because if we round up, we're guaranteed we're going to have enough. If we round down, our sample size now isn't big enough. Right? If I just did 335, that's not as big as what the formula says I need. But 336 is. It's even bigger. But in this case, bigger is better. So what might change here, Ashton? Because like I want to set you up for any kind of problem, not just this specific one. So things that are going to change. The z-score. That's going to change depending upon the confidence level.
Okay.
Okay, so confidence level determines your z-score. The error bound, that's going to change because you might have a different amount of acceptable error. So I'm going to put there acceptable error. So, right, if they say you want to be within 2%, okay, so that's going to be 0.02. You need to be within 8%, 0.08, whatever, right? So that's going to change. And then the third thing that might be different is your P. I guess P and Q both change together. But P, this would be your estimate of the proportion. In this case, we weren't told one, so we went with 50%. But if you're told one, you go with that as your P, and then Q is 1 minus that. So let me actually write that over here too, that Q is equal to 1 minus P prime. So that's how you get that in general.
Okay.
So let's go back to the homework. Goodness, where do I have that? Oh, because I switched to the book. Here we go. Okay, so let's come back to this one, just so you can see how things might be different. Okay, so like let's look at this first one. So political candidate is asked to conduct a poll, wants a margin, 3% margin of error. So that's our EBP is now going to be 0.03. We have a new confidence level, 99%. So we're going to have to take the possibility of being wrong, which is 1%, divide that by 2, so 0.5%. So we need to find the z-score for 0.5%. So you do inverse norm with the area of 0.005.
Okay.
Right? But again, do we know anything about what percentage we are expecting? The answer is no.
No.
So we're going to use 1/2 for P prime and 1/2 for Q prime.
Okay.
So the same thing's going to happen for number 3. But now check out number 4. So number 4 here, it's based on previous evidence. You believe the population proportion is approximately p equals 0.84.
So would you just do the same formula but plug in 80.84 for the proportion? Yep.
So p prime is going to be 0.84.
Okay.
And q prime is going to be 0.16.
Okay.
Because that's what you get when you subtract this from 1.
Mm-hmm.
So when you actually have an idea of what the proportion is, it decreases the n. It actually makes it easier for you. It makes it a smaller n value than if we just go with the guess of 1/2. But there you go. So we would put that in for our p, change our q, 90% confidence level. Okay, so alpha is 10, alpha over 2 is 5. Our error bound is going to be 0.02, and just, again, plug it in.
Okay. Okay, I think I know how to do this now.
All right.
It's a whole lot simpler now that you because I'm a very visual learner too. So like I have to see what I'm doing. It just can't be told to me, you know?
Right.
I don't know.
And
I'm very like
it's good to see that like this step, then the next step, then the next.
Yeah, definitely. I have to be able to do it on my own too. Like I have to be able to give myself an example problem and then be able to do it, and then I'm more confident that you know, I could get the right answer from my knowledge.
And every time you do one and you get it right, it's going to make you feel a little bit more confident. And
it's so satisfying too, because you're like,
right?
Oh man, I did that on my own.
And you get the green check mark and you're like, yes.
Yeah, it's awesome. Okay, thank you.
Yeah, you're welcome. Thanks for asking that question. That was some good review.
Yeah,
so it looks like we're pretty much out of time. So I'm going to stop the recording.
Okay.